In this chapter, we will be looking at various types of functions. In this lesson, we will be analyzing rational functions and looking at points of discontinuity.
Okay, so before we get into the meat of this lesson here, just to review real quickly, when you've got a rational function here, your vertical asymptote is a result of a non-permissible value in the equation of the rational function. Okay, so your x equals h here, this is your non-permissible. Now, although I've said this before here, I'm going to just say it again here. I call this an essential, okay, an essential discontinuity, and you're going to actually get to see why I call it this in this particular lesson here. But this is a non-permissible value that exists in the function, and you can't kind of get rid of. It's there, you're stuck with it. Anyway, and you'll see the contrast to that in just a few minutes here. Your horizontal asymptote is going to correspond to a value that the rational function approaches. As the values of x get larger and larger, whether that be in the positive or the negative direction, for very, very large values of x, the horizontal asymptote is basically this value that the function approaches, y equals k. Now, here we go. So with that being said, we're going to move on here and talk about another way that a non-permissible value can affect the graph here. Because, as it says here, not all of them result in a vertical asymptote. Some of them result in just what we call a point discontinuity. Now, to be fair to some people at the university here, when we talk about point discontinuity here, our intention here in our curriculum is maybe not quite in line with what they'll talk, the way they'll discuss it at universities. At a university, they'll refer to a point discontinuity as being basically any specific number along the x-axis there being a point where the graph becomes discontinuous. And so that could be the same as a vertical asymptote, or what we're about to talk about here. For us, when we talk about a point of discontinuity, what we're referring to here is a point on the graph where the function just ceases to exist. Basically, it's this open dot, okay? It's this hole, if you will. A hole in the graph. Okay? Not like an asymptote. An asymptote, the function kind of swoops out like this or swoops up like this. This is a hole, like an empty dot on that graph here. And it occurs when the function can be simplified by reducing a common factor, and this is the key here, a common factor shared in the numerator and the denominator, okay? That's how you know you've got this. So if you've got, for example, here we'll zoom in a little bit so this is quite clear. So you've got some function here, and it's going to be x minus a times blah 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 over x minus a times blah blah blah. As soon as you've got this shared factor there, you are going to get a hole in the graph, a point discontinuity. Okay, is what we're going to call it here. Now, some other things to know here. The missing single point is represented by an open circle, considered a hole in the graph. So we're going to draw the line there, put a little open dot there, and away we go. And that's going to represent my point discontinuity. Now, so here's kind of the build up to this. Okay, so we're going to zoom in again here. If the rational function written in simplest form, and the function, is written in simplest form, and the function is undefined for x equals a, then it's a vertical asymptote. So really important, two things here. It's in simplest form. So you've factored, you've canceled, and you're still getting this non-permissible here. That's a vertical asymptote. If it's in simplest form, you've eliminated everything else that's shared. Again, this is what you're left with here. This is what I would call an essential discontinuity. Okay, because you are stuck with it. Here's a good example here. I've got x over x minus 3. X equal to 3 is a vertical asymptote. There's nothing I can do. I am stuck with that non-permissible value down there. I can't cancel anything out here. No, please. You should know you cannot cancel those two x's there. That's not possible. That is, if you're doing that, you're doing the order of operations in the wrong order. This bar implies a set of brackets here. Before I could do that kind of division, I would have to subtract 3 from x. Well, I don't know what x is, so I can't subtract 3 from it, so I'm stuck here. I'm stuck with this operation. I need to do that subtraction before I can cancel. That's as simple as it's going to get. And so you get a graph that looks like this. Okay, with this vertical asymptote at x is equal to 3. Now, compare that to a situation here where there is a common factor both in the top and the bottom. Okay, then there is a point discontinuity at that value of x, and this is what we call a removable discontinuity. Okay, you can actually get rid of it, and because you can get rid of it, in a sense, I'll explain that in a second here, because you can get rid of it, it becomes this little dot, this little hole in the graph, okay, as opposed to what we get here with an essential discontinuity, which ends up being this gigantic hole in the graph going from infinity to infinity here. Now it works like this. Let's say that you've got x plus 2 times x minus 1 over x plus 2. Okay, what I want you to understand by this is, okay, so we started off with x plus 2, x minus 1 over x plus 2, okay? So we get it down to here, and before we cancel this, I want you to know here that what we're going to do here. When we divide this out, x plus 2 divided by x plus 2, the answer is going to be 1. If you plug 10 in for x, you get 12 divided by 12, that's 1. If you plug 8 in, you're going to get 10 divided by 10, that's 1. If you plug 3 in there, you're going to get 5 divided by 5, that's 1. However, when you plug negative 2 into this, you get 0 over 0, and that's not 1. That's undefined. Okay? So what happens here is this particular function here, okay, in this one right here, is going to be undefined. Okay, this is undefined at x equals negative 2. Now, but for every other value of x, those two are going to cancel. Okay, for the infinite number of different values you can plug in there for x, that's going to cancel. This is going to be the same as this. But because this is undefined at negative 2, and this isn't, okay, this is actually, the best you can say here is that this function right here is not, it's not actually equal to x minus 1, it's equivalent to x minus 1. They're not exactly the same because at x minus 2 this is undefined, but at x minus equal to negative 2 here, at x equal to minus 2, this isn't, this becomes negative 3. So these aren't exactly equal. Now, I can make them equal by simply stating that x cannot equal negative 2. And as soon as I do that, now this expression is equal to this expression with this little added little bit here. And this is what I mean by a removable discontinuity. Okay, because notice here, for this function right here, up to this point, this, I'll even write this in here, f of x. For this function right here, there is a non-permissible here. Okay, x cannot equal negative 2. But I'm allowed to do this little bit of canceling and it becomes equal to this. This doesn't have that non-permissible anymore. It's gone. So I've removed it. The problem is they're not exactly equal. Okay, they're not exactly equal. So what I have to do is I have to state that x can't equal this this value right here, and now they're equal. But now let's think about this. F of x equals x minus 1. That's just a line, okay, with a y-intercept of negative 1 and a slope of 1. And it would be, it would cover everything. It's got a domain that's all reals, a range that's all reals. But when I put this little bit into it, what that does is that erases the dot right here at negative 2, puts a little hole there. So that's the graph of this particular function right here. Okay, so like it says here, the original function is undefined for x equals negative 2, but since you can cancel it out, you can remove it, okay? And what you're left with is the line here. It's called a removable discontinuity, but again, we kind of keep saying this. In order to make this expression equal to its simplified form, you have to state this, and this is identifying where the hole is. And that's how these point discontinuities work.
Analyze and sketch the graph of f of x equals x squared minus 5x plus 6 divided by x minus 3.
Okay, so we're going to start by just walking through an example together here. The function f of x is equal to x squared minus 5x plus 6. This is divided by x minus 3. There's my rational. But we can simplify it like this. The numerator here can be factored down into, if you want, x minus 2 x minus 3 all over x minus 3. Here's my f of x. This is exactly equal to this. Okay, not a problem. But notice that there's this shared factor, this x minus 3. Now, just like we were arguing before, you can plug any number you want into that. 10, negative 3 minus x, 10 minus 3 over 10 minus 3, 7 over 7 goes to 1. Plug 20 in there, 17 over 17 is 1. Plug 6 in there, 3 over 3 is 1. The only number that you can't plug into that and have it become 1 is positive 3. If you plug positive 3 into this, you get 0 over 0, and that is undefined. So here, this is undefined at x equal to 3. Now for every other number, I can just cancel those out like you're seeing here, and this becomes this bit right here. Now, just like I argued before, this actually is not equal to this. Because they aren't. Although they are the same for like an infinite number of values, they are not the same at all values because they're not the same at 3. You plug 3 into this, you get 1. You plug 3 into this and it's undefined. So these are equivalent. We'll use this little symbol right here, equivalent. Here, maybe just zoom in a little bit. Okay, this guy right here. Now, if I pause for a second and say, yes, it's equivalent to this, except I can't let x equal positive 3, as soon as you do that, as soon as you state that, now they become equal. Okay, this together with this restriction makes it equal. Now, let's talk about this. This function right here, x minus 2, that's a linear function, it's a straight line. Now it's going to look like this. Now normally what would happen is it would go right through here, okay? So it would look like this function right here, y-intercept of negative 2, slope of 1. However, remember, we said that this is going to be equivalent to x minus 2. But then we include this little restriction here where x cannot equal 3. That makes them equal, but it also introduces that hole right there. Okay? So, now if you want to find the value of the point of discontinuity, okay, the y-coordinate, what we're going to do here is we're going to utilize the fact that that thing is basically equivalent to x minus 2. Okay, because it really is. It's just that one number where they're not equivalent to each other. Let's figure out what that one number would have been. Okay, even though it doesn't exist there, we figure out what that is. And if you plug 3 into it, okay, so we substitute in here a non-permissible, okay, and plug that in. 3 minus 2 is 1. So what we've got here is this point discontinuity is happening at the point 3 comma 1. And actually, when you look at our graph there, yeah, that's exactly where I'm seeing it. X equals 3, y is equal to 1, right there. Perfect.
Analyze and sketch the graph of y equals x squared plus 2x minus 8 divided by x squared plus 5x plus 4.
Okay, so with this question right here, we're going to do the full meal deal. We're going to do everything. So let's zoom in on that question there. So we've got y equals x squared plus 2x minus 8 over x squared plus 5x plus 4. Now, first thing we got to do is we got to factor this. So that is going to be, and I know it's going to be binomial times binomial over binomial times binomial, because this is a quadratic times a quadratic. I also know, based on the leading coefficients, this is going to be x and x, x and x. Okay, so factors of negative 8 that differ by positive 2, plus 4 minus 2. Factors of 4 that add to 5, that's going to be plus 4 plus 1. Okay. So this expression right here is exactly equivalent to this because factoring doesn't change anything. Now, this is going to be equivalent, okay, to x minus 2 over x plus 1. They are not equal to each other until I make this little statement right here, until I say x cannot equal negative 4. And as soon as I do that, they become equal to each other. Okay, so I identify this little gap right here. Now these two expressions are equal to each other. Now, someone's going to argue here, well, wait a minute, shouldn't I also say that x cannot equal negative 1? Well, actually, yeah, you should. But this is an essential discontinuity. It stayed, this little thing here survived to the end. This one I was able to remove up here, so I need to state it because it's gone from this expression. I can look at this and tell you that x can't equal -1. So I don't really need to state that. However, I sense that you're probably going to be expected to do that. Okay? So it's not absolutely necessary to write that x cannot equal -1 because I can see it right there. It can't be, but yeah, you probably should just do that anyway. Okay, so now let's take a quick look at this. Vertical asymptote. The vertical asymptote comes from the essential discontinuity, the non-permissible that survives to the end after simplifying, and that, in this case, is -1. So vertical asymptote x equals -1. The horizontal asymptote, well, we're going to compare leading coefficients, right? We're going to compare the highest degree terms. So what I do here is I just cancel all the rest of that out, don't really care about it. And in this case, it's very straightforward because you're left with x squared over x squared. That's just going to be 1. So my horizontal asymptote is y equals 1. Now, my point discontinuity is going to occur here, okay, at the non-permissible that I have to state because it's missing now from the final expression. So that's going to occur where x equals -4. Now, I can finish this off, I can figure out what the y-coordinate is by simply taking this point right now and plugging it in. Because remember what I said, the -4 is not a non-permissible in this simplified form. I have to state it because I've made it go away here. So plug -4 in, -4 minus 2 is -6. -4 plus 1 is going to be -3. -6 over -3, 2. So the y-coordinate is 2. All right, my x-intercept. Okay, let's go back up here. My x-intercept is going to occur, now here's my simplified form right here. It's going to occur where the numerator goes to 0. Okay, because remember, the denominator cannot make this expression equal to 0, just the numerator. Think about that, and we're going to get that 2. Okay, when x is equal to 2, that's when the numerator goes to 0. For the y-intercept, well, the y-intercept, we just have to basically cover that up here, right? When you plug x in for 0, all of this disappears, and so we're left with -2 over 1. So our y-intercept here is going to be -2. Okay. The domain. Now, you got to remember what I said before about horizontal asymptotes and vertical asymptotes here and whatnot. Although you can never cross vertical asymptote, you can sometimes cross a horizontal asymptote, but in this context, in this course, no, we can't. So our domain, quite simply, is going to come from the vertical asymptote and the point discontinuity. So x cannot equal -1 or -4. That is going to be really consistent. The other thing that's going to be consistent here, although not for all questions in mathematics, but in this course, yes, the range is going to come from the horizontal asymptote and the point discontinuity. So 1 and 2. And that will become a lot more clear when we take a look at the graph. So here we go. So we've seen that this thing has a vertical asymptote at -1. So I'm going to draw a dotted line here to represent that. I'll make it kind of thick here. Okay. We also saw that it had a horizontal asymptote at y equals 1. Now that's this right here. Okay. It had an x-intercept of 2. That's right there. A nice big dot for that one. Y-intercept of -2. There we go. And then it had the point discontinuity at -4, +2. So open dot right there. Now, based on where these dots are located, that's indicating to me where the graph is located. And I already know that when you've got this, like a rational expression with one, okay, with one vertical asymptote, one horizontal asymptote, it's going to have that hyperbola shape to it that I mentioned before. So here, this is going to approach the vertical asymptote from the right, come up, swing through those 2 points, and then it's going to approach the horizontal asymptote from below. Here, it's going to come down from the vertical asymptote. It's going to go and hit that point discontinuity and then keep on going. Okay, so like we said before here, notice that we've got this break in the range at the horizontal asymptote, but it's also a break in the range at that point discontinuity. There's a break in the domain at the vertical asymptote, and that point discontinuity is also showing us a break in the domain.
Complete the following table.
All right, well, so we got a lot to do in this table here, and we're going to go across the rows here for each of these. Before we start answering these questions, though, what we got to do here is we got to factor everything here. So this first one, in the numerator, we'll take out that x. We're going to have x plus 5 there. Now, at this point here, you can be pretty sure that we're going to repeat one of those factors here. So I'm guessing x plus 5, and if that's the case here, then this other factor has to be x plus 2. So those are going to cancel. I will come deal with this in just a minute. I needed to see that in factored form first. Here, what do we got here? We got a positive 12, and that's going to negative 7. So this has got to be negative 3 and positive 4 as my factors. And then the denominator is a difference of squares, so x minus 3, x plus 3. Okay, and then I can see again those two are going to cancel. Here, actually we've already seen this one in this lesson. This is going to be x plus 4, x plus 1, all over x plus 1, and then those will cancel. Over here, this one here, x minus 3, x plus 3. Notice that there's no overlap here. There's no doubling up those factors, numerator denominator. So this one here is not going to have a point of discontinuity. It's kind of an interesting one. Okay, so now let's come across here and we're going to take a look at the vertical asymptote. The vertical asymptote is the non-permissible that survives. It's the essential one, the one that you can't get rid of. It survives to the end after simplifying. Well, I'm going to get rid of the x plus 5s here. And so this is going to end up being x over x plus 2. And so my non-permissible will be x cannot equal negative 2. That's my vertical asymptote. Here, this one's going to be x plus 4 divided by x plus 3. The non-permissible that I'm stuck with at the end is going to be x can't equal negative 3. That's my vertical asymptote. Here, this is kind of an interesting one. Notice that once I've simplified that, there's no more denominator. It's gone. There is no vertical asymptote there. This last one, nothing canceled, and so both of the restrictions there will be essential discontinuities, and then therefore vertical asymptotes. So x is equal to 3, x is equal to negative 3. Okay, there we go. Now, come across here, horizontal asymptote. Okay, well let's make sure we can look at the function here. So again, with the horizontal asymptote, I get rid of all the secondary terms there, tertiary terms. I'm only concerned with the first term in numerator and denominator. X squared over x squared simplifies down to 1, so y equals 1. Second one here, same thing. I'm going to get rid of those guys. I'm just left with x squared over x squared, which means I'm going to get a horizontal asymptote, y equals 1. Here, okay, when you get rid of the everything other than the highest degree terms in the numerator and denominator, we're left with x squared over x. Now, if you simplify that expression right there, you're just going to get an x in the numerator, and as x gets larger, okay? That whole expression is getting larger here. Essentially, the numerator is growing way faster than the denominator. Turns out there will be no horizontal asymptote. That's kind of interesting. Interesting behavior in this one. Here, notice in this case here, if you drop off every other term here, you're left with 18 over x squared. Well, as x gets larger, okay, this whole fraction here is going to get smaller. It's going to approach 0. So again, my horizontal asymptote is going to be 0. Now, coming over here. Point discontinuity. This is going to occur, okay, from the restriction that I was able to factor out here. So this is going to occur when x is equal to negative 5. Now we're looking for the point of discontinuity, so I want to know the y-coordinate too. So I'm going to take this and plug this into the simplified form. Negative 5 over negative 5 plus 2. Well, negative 5 plus 2 is negative 3. So that'll be over 5/3. Oh, sorry, not over 5/3. Negative 5 comma 5/3. This guy right here, the non-permissible that I was able to kind of cancel out was positive 3. And if you plug positive 3 into the expression that remains, you're going to get 7 over 6. So positive 3 is my x-coordinate, 7/6 is my y-coordinate. All right, here, this one did have a point discontinuity because those things, the two factors here, x plus 1 over x plus 1, disappear. The non-permissible that we got rid of there was the negative 1. And if you plug negative 1 into what remains, you're going to get positive 3. Now, over here, there was no shared factor, so as a result, there's no point discontinuity in that last expression. All right, we keep going here. The x-intercept. Okay, the x-intercept occurs, remember, where the numerator goes to 0. And in this case, the numerator goes to 0 when x goes to 0. There we go. X is 0. X-intercept occurs where the numerator goes to 0. Doesn't matter about the denominator. Denominator won't affect that. The numerator goes to 0 at negative 4. There's my x-intercept. Again, this occurs where the numerator goes to 0, and the numerator in this case, just like the previous one, is x plus 4, so negative 4. Now this is kind of an interesting one here. The expression in the numerator, well, it's just 18. It never does go to 0. It can't. There's no x there, so it doesn't go to 0. So there's a blank right there. All right, the y-intercept. The y-intercept is calculated by making x equal to 0. So let's go up to there. If we make x equal to 0, we will get 0 over 2. That is just 0. For this next one, if we make x equal to 0, we're going to get 4 over 3. There's my y-intercept, 4/3. Here, if we make x equal to 0, we just get 4. There's my y-intercept. And for this one right here, if we make x equal to 0, and in this case it's actually easier to look at from the original, we're going to get 18 over negative 9, negative 2. Okay, now let's finish this off here. Our domain and our range, domain and our range are going to be linked to the asymptotes and the point discontinuity. So in this case here, we've got x cannot equal, y cannot equal. This is the easiest way to write these expressions here. So x cannot equal negative 2 or negative 5. Okay, those are coming from the vertical asymptote, point discontinuity. Y cannot equal 1 or 5/3. That's the horizontal asymptote and the point discontinuity. Next one, x cannot equal, y cannot equal. Let's go back up here. Vertical asymptote, negative 3, can't equal negative 3, but it also can't equal 3 from the point discontinuity, so it can't be negative 3 or 3. Okay, our horizontal asymptote was 1. And from our point discontinuity, we get 7/6. So y can't equal 1 or 7/6. For this next one here, the asymptotes disappeared. So actually our restriction is a little simpler here for domain and range here. They're both coming from the point discontinuity. So x can't equal negative 1, y can't equal 3. And for our last one, it's the reverse is true. There is no point discontinuity, so the discontinuities are simply coming from the asymptotes. So in this case here, my domain is x cannot equal 3 or negative 3. And for our range here, y cannot equal the horizontal asymptote, 0. All right, let's take a quick look at that. There we go. All sorts of work here, but the key to understanding all of these things here really is to factor everything first. That has to be your first step when you're approaching these rational expressions.
Write a simplified equation for each rational function in the form y equals f of x divided by g of x.
All right. Well, to come up with the equation of this function, or this rational expression here in this form, f of x over g of x, it kind of requires me to think backwards some of the steps that we've taken in the previous questions here. So the way you want to take a look at this one in particular, this one right here, is to remember here that the denominator, the g of x, where the denominator goes to 0 is going to produce my my vertical asymptotes. Where my numerator goes to 0 is going to produce my x-intercepts. So let's just take a quick look here. I've got a vertical asymptote here at x equal 4. So my denominator is going to be x minus 4, because that's going to be, when that goes to 0, that's my vertical asymptote. My x-intercept here appears to be negative 2. X equals negative 2, which means the numerator must be x plus 2. Okay, that's when that goes to 0. So what I'm going to do here is make it look like this. Y equals, I'm going to put a vertical stretch in there, and I'm going to have x plus 2 divided by x minus 4. Now, I'm not really too sure of another point here that goes through that. There's nothing here that's specifically clear. However, that point 1, negative 1 looks pretty good here. So if I plug 1, negative 1 into that, okay, that's that point right there. That looks like it's going through there kind of cleanly. So it's going to be negative 1 is going to equal a times 1 plus 2 over 1 minus 4. And so negative 1 is going to equal, okay, a times 3 over, oh, look at that, negative 3. Okay. Oh, okay, bring that up here. We're going to get 3. So a is going to equal 1. So the equation that we're looking for here, actually that simplifies down. That must have been on there. That worked out really nicely. X plus 2 over x minus 4. Now I'm going to double check this by simply checking to see what my y-intercept here is. If you let x go to 0, we're going to get 2 over negative 4, so negative 1/2. Now let's take a quick look at the graph here. And actually that's perfect. That looks exactly like my answer there. There. I feel very confident that the function here is x plus 2 divided by x minus 4. All right, coming up with the equation of a graph that looks like this is actually a fair bit easier than the previous one here, because my result here is a straight line. Now I'm just going to ignore the fact that it's got that point discontinuity in it right now. We'll take a look at that in a second here. I have got a graph that appears, okay, I'm going from negative 6 up to 6 here. Now the scale is a little bit off just because of the way it's drawn here, but that means this thing's got a slope of 1 and it's got a y-intercept of negative 6. Okay, so that means that this graph here is looking like this. It's going to be x minus 6. Now, I know that it's got a point discontinuity here at negative 1, which means this must have had an x plus 1 in the numerator and denominator that canceled there. Now, additionally, actually, sorry, I think I've already kind of dealt with that, sorry, with the x minus 6 here. I was going to put a stretch factor in the front here, but the truth is I already know, based on the equation of the line, that it's going to go through that point right there. So actually, that's it. I've completed my mission here. What I might want to do here, though, is expand that out just because it looks a little bit better. So it's become x squared minus 5x minus 6 all over x plus 1. And that's the equation for this particular function right here. All right, now this rational expression here, this rational function here, has got bits and pieces of the previous two questions in it. So to start off with, first of all, I'm going to notice that, actually, so I'm not going to write that right now. I'm going to deal with the pieces that I need to look at here. I know right now that I've got a vertical asymptote at x equals 1, which means my denominator is going to go to 0. It's at 1, it's got to look like this, x minus 1. I also know right here that it's got an x-intercept of negative 1, so I know x equals negative 1 is the x-intercept. Bring that over. X plus 1 equals 0 has got to be in the numerator. Okay, this is like the question A here. So numerator, this has to be in the denominator. At this point, I'm not 100% sure of the stretch factor. Okay, I've got this negative 1 right here, so what I might do right now is, let's figure that out here. So y is equal to a times, this has got to be x plus 1 over x minus 1. Now, I know I'm not done yet. Someone's going to cry foul here because there's something else going on here. Just hold on a second. This thing looks like it's got a y-intercept of negative 1, so it's going to go through the point 0, negative 1. And so if I plug negative 1 in, a, it's going to be 1, negative 1. Looks like a here should be equal to 1. Okay, good, good, good. Now, this is going to give me the function here, y equals x plus 1 over x minus 1. Now I'm going to take into account the fact that I have a point discontinuity at x equals to 3. Okay, so that means I must have had an x minus 3 over an x minus 3. It had to be that factor had to show up in the numerator and denominator here. Now, how do I double check to make sure that this is actually the correct function here? Well, we already know that these are going to cancel for the most part here. Let's just take a look at what happens if you plug 3 into what's left over here. If we end up getting a y-coordinate of 2, that's a pretty safe bet that this is correct here. So 3 plus 1 is 4, 3 minus 1 is 2, 4 over 2 is 2. There it is. So that is the correct function here. Now, what we might want to do is expand this out just because it, I don't know, looks kind of cool that way. So negative 3 plus 1, negative 2x minus 3. And this is going to give me x squared, what's that going to be? Negative 4x plus 3. There you go. All right, this question here doesn't give us quite a lot to work with here, but should be enough here. So vertical asymptote at x equals negative 2. Now this means that has to show up in the denominator. Additionally, we've got this 5, this point discontinuity at 5 comma negative 1/7. Now that 5 there, x equal 5, means that x minus 5 equal to 0 has to show up in the numerator and the denominator. So right now my best guess at what this function looks like is going to be x minus 5 over x plus 2 x minus 5. Now I don't know if that's right. Okay, there may be a stretch factor here. So what I'll do here is I'll put y equals and I'll put an a up front here. Now the reason I'm doing that here is because I know that these are going to cancel here, but I know that if I plug 5 into the answer here at the end, I should be getting negative, whoops, sorry, you can't see that, negative 1/7. So negative 1/7 is going to equal a over 5 plus 2. Well, there's my 7 here. Oh, this only works if a is equal to negative 1. Okay, whoops, negative 1 here. So therefore, I can write y is equal to negative x minus 5 all over x plus 2 x minus 5. Now, if we really want to, and you don't really need to, but if you really want to, you could multiply that out. Negative x plus 5 over x squared minus 3x minus 10. And the only reason I multiply that out here in this case is because I've done it in every other case. Might as well do it here too.